Hey everyone, I'm Nick, and this is Bits of Architecture. So in this episode of the series, we're going to have an introduction to instructions. So as we've talked about in previous episodes, our computers understand instructions, right? Instructions are just the language of our processors. And we can think of instruction sets as being the vocabulary. So our processors can perform a fixed number of operations, and those are exposed to us through these instruction sets and these instructions. And this is a constraint that we have to work within. So if we're writing a program, directly in assembly, or we're using a compiler to generate the assembly, from a high-level language like C++, right? We both have to work within this constraint of, we can only create our program using the instructions from our instruction set. Now, there are a number of different instruction sets out there, and they all have their own design trade-offs. So the one that we're going to be focusing on in this series is RISC-V. But there are also things like x86 and MIPS and Power and ARM and all kinds of instruction sets for dedicated accelerators. Now, during all this, it's important to think about this stored program concept, right? This idea that our instructions and data can be stored in memory and are easy to change. So a nice thing to think about here is this idea of bits are bits. So at the end of the day, our instructions are just bits stored in memory. So we just encode our instructions as ones and zeros, and they get stored in memory. And that chunk of memory with all those ones and zeros, we consider our program. And things like our data, so pictures or audio or numbers or strings, those are all just ones and zeros stored in memory as well. We're just choosing to interpret them as, say, a picture or a string. And we can swap out either of these things as needed. So if we want to run a different program, we just load a different set of ones and zeros into our memory. And likewise, if we want to work on different data, we just load in a different set of ones and zeros into our memory. Okay, so let's talk a little bit about the difference of high-level languages and instructions. So our high-level languages generally allow us to be fairly expressive with the code that we write. So for example, if we want to sort something like a vector in C++, we can just use something like a call to std sort, which we typically don't have the same level of expressiveness in our instructions. So our instructions are generally primitive operations by comparison. So just things like add, multiply, divide, things like branches and comparison operators. Now, even though, we have these primitive operations, compared to high-level languages, we can still synthesize something like a sort out of just primitive operations. So we can still be general in terms of the applications that we can run with the instructions that we have. Now, there's a number of reasons why we have primitive instructions. A good reason is that something like std sort would be very difficult to implement in terms of hardware, right? So we wouldn't want to necessarily spend the time and resources in silicon to implement such a complex operation with a dedicated instruction, when we can just synthesize it out of much easier to implement simple instructions. Likewise, we have to be somewhat cautious in terms of, how specific we're going to be with the instructions that we implement. Right, at the end of the day, that's going to take up some silicon on our processor. And, we have to make sure that the programs that are going to be running on our processor actually have a use for that instruction, right? If we, implement an instruction that's never used, it's kind of pointless. Now, we can see kind of this difference of high level versus low level and synthesizing, a high level kind of compound operation C++ out of these primitive operations with just a simple example. So for example, in C++, if we want to set A equal to B plus C plus D plus E, right, we could just do this very simply on a single line. But in something like assembly and our instructions, we often don't have, say, something like an add that takes an arbitrary number of inputs. So maybe we only have an add that, say, has 2 inputs and a single output. So here, just to add these 4 numbers together and store it into A, we'd have to do something like these 3 instructions here, where we first add B and C and store that partial result in A. Then we add A that has that partial result with D and store that partial result in A. And then finally, we add our partial result with E and store that final result in A. So it takes us 3 assembly instructions to do the single line, say, of C++. Now, another important thing to keep in mind is that our instructions typically use registers. So when we're doing something like these add instructions here, we're operating on values being stored in registers. And registers are just these pieces of memory that are within our core that our instructions typically operate on, right? And we typically have a fixed, or rather we have a fixed amount of them in our core, so something like 32 registers. Now, of course, we can't fit all of the data in our program in 32 registers. Our registers are typically only, say, 32 or 64 bits in length. So the rest of our data is stored in memory. So we have to have instructions to say, move things into registers from memory and take things from registers and put them back into memory, right? So we have to have different kinds of instructions. Which brings us into, very naturally, into these different classes of instructions we can kind of group things in. So at the very top, we have, say, things like arithmetic instructions, and these are fairly intuitive, things like adds and subtracts. Then we have things like data transfer instructions. So like I said, we have to move things into registers from memory and then out of registers into memory. So those will be our loads and stores, so something like a load word instruction. Then we have, say, our logical operators, so things like logical and or logical or logical exclusive or, right? We have those kinds of instructions. Then we have our shifting instructions, so we're shifting the bits inside of our registers. So, logical shifting and arithmetic shifting, both left and right. And then we have things like control flow. So typically our programs don't run every single instruction from top to bottom, just like we write in, say, high-level languages like C or C++. We often jump around in our program. We have, say, function calls, we have if, else statements, we have switch statements, so we're selectively executing a number of our instructions. So we have to have things like conditional branches, so where we jump to some location in our program based on a condition. Likewise, we have things like unconditional branches, so where we just jump to some point in our program. So that would be something like a function call, right? An unconditional branch. Okay, so before we wrap up, we should talk a little bit about some of the design principles we have when we're thinking about our instruction sets. So number one is this idea that simplicity favors regularity. So our hardware can be much easier to implement if we take a fairly regular structure to our instructions. So for example, if all of our instructions, say, have 2 operands and 1 result, that allows us to make our hardware more simple. Another one of our design principles is this idea that smaller is faster, right? So why don't we have, say, 2048 registers or 4096 registers? Well, the fact is that accessing larger structures takes a longer amount of time. So that might have negative consequences in terms of our clock rate, right? So if we have such a large structure, we may not be able to clock our processor as high or at as high of a frequency. And then our final design principle, which kind of relates to the previous two, is this idea that good design demands good compromises. So, what exactly do we do about the length of our instructions versus, how we encode our instructions, right? Can we get away with a fixed length and different encodings, or do we go with the same encoding for all of our instructions, but have a variable length of instructions? So these are design decisions that we have to make. Likewise, how many registers do we have in our processor? Do we have 32? Do we have 48? Do we have 64? These are all design decisions that we have to make along the way when we're talking about our instruction sets and really all things in computer architecture. Okay, so that's going to go ahead and do it for today. As always, I'm Nick, and hope you have a nice day.